So now the Z80 CTC counter timer chip has been added up here, and it's running a program currently where the counter timer chip is interrupting the CPU. Every time it does so, it increments the accumulator and then displays it on these LEDs up down here, which are the upper address bits. CTC is going to be using this circuit mainly to provide the baud rate to the SIO, which is a serial communication chip, which will go in here. So in this video, I'll go through the program which is actually currently running, how to program this Z80 CTC, and then I'll go over the circuit diagram and how this Z80 CTC is wired up to the Z80 processor. So this is the program to control the counter timer chip for the Z80. At the top I need to allocate some stack size for the program because it will be using interrupts, and when it goes into an interrupt it needs to store that on the return address on the stack so that it can return back into the program after it's finished performing the interrupt. Then I've got the 4 addresses of the counter timer registers, one for each of the timers. And then I'm only using timer 0, so I've got the configuration byte for timer 0 and the count value for timer 0. When the count value is 0, it counts 256. So when it's value 1, it counts 1. When it's value 5, it counts 5. But the 0, it counts as a 256 value. So at the beginning of the program, I set the stack pointer to the high point of the stack. So if I scroll down, I've got the label down here. So the stack works from high memory. Then as you put things onto the stack, it goes down further and further down into lower memory. And I've put these values up in the upper part of the first page of memory. And the reason I've done that is because in the top word where I've got there, I'm going to be displaying using the LEDs on the computer to actually display the accumulator value. So I don't want to put any other values onto that upper address word by mistake. So I'm keeping this whole program in the lower page of the actual computer. So after I've set the stack pointer, I then have to place the interrupt vectors. So the way that the interrupt vectors work on the Z80 is so there's about 3 different modes that you can have the Z80 in for interrupts. I'm going to be using interrupt mode 2, which is set there, and that's the mode which all of the support chips for the Z80 operate in. And with that, there's register I, and the register I forms the upper part of the interrupt vector, and then the actual device itself provides the lower part of the interrupt vector when it actually produces an interrupt. So here I'm setting the upper part of the interrupt vector to this label infect, which is down bottom here, which will be the upper word of this, which is 0. So I set it there into the I register. Then I load up the value for the interrupt vector which it's going to supply to. So when I'm giving the device here the actual interrupt vector which it needs to provide for CTC 0. So and that's this interrupt vector here, and I have to program that into the device so the device knows what interrupt vector to actually provide when counter timer 0 actually triggers. And then counter timer 0 configuration word, so you can set up like divide by 256, 16 interrupts enabled, that kind of thing in this configuration byte, and then you send this to the register for counter timer 0 on the CTC. And then the third byte you have to send is the actual counter timer value, and you send that to the CTC. And then channel 0 is ready to start producing interrupts, and it will do so. So in the actual main loop of the program, I put the accumulator into the upper byte of the HL register, which is seen here. And what that does is, so consider the H of this register to be what the accumulator value is. And all it does is read from memory pointed to by HL into D, and this is the only instruction in this program which actually reads or does any performs any function on the upper memory area, anything above 256. So then that's what displays the LEDs on the actual computer itself, and that just goes in a tight loop. So all it does is continuously display the accumulator on the top byte of the address LEDs. And then we've got the actual interrupt itself. So you define the interrupt routine, and all that does is increment A. So every time this interrupt occurs, the display will actually update with the new value of A, because it's in a tight loop there. And then after you finish the interrupts, you have to enable interrupts with EI. And I've got the other interrupt vectors here, just in case they trigger. They shouldn't do, but this is one of the things you do in programming, is you do fail safes, because you don't just leave the interrupt vectors of all the other counters, timers, to be random. You have to. It's best to actually provide a location where they are, just in case they trigger. And then return from interrupt is all it does as the last step. So this is the Z80 CTC in circuit, and on the right hand side, all 4 counter timer ports are taken out. And so each port consists of a trigger. So in counter mode, the trigger will increment the counter in the CTC for that particular channel, and an output. So in counter or timer mode, when the counter gets down to 0, it will output a pulse on the output pin. The only port that doesn't have an output pin is port 3, and the reason for that is because apparently there's no more pins left on the device, so there wasn't enough pins to put an output for channel 3. All the other pins, all these ones, these are just connected directly to the Z80 pins themselves. The interrupt pins, so the interrupt pin itself goes to Z80, and then the IEI and IEO are a daisy chain, so they're connected together between these peripheral devices, so that it sets a priority as to which one gets the most important interrupt. And then there's just the addressing. So chip enable provides the highest, the main part of the address, which is port 80. I've put it on, and then CS, which I thought was chip select at first, because that's normally what CS is, but it's channel select on the Z80 CTC. So that's their 2 addresses which are used to select the channel. So A0 and A1, which provide channel 80 for port 0, 81 for port 1, 82 for port 2, 83 for port 3, and so on. And I've got, for the decoding of the main address, I've got a HCT138, and that decodes address lines 2, 3, and 4, 5, 6, and 7 to provide 8 ports, which can be used for I/O peripherals. And it also provides a way of, because these chip select addresses can be altered for each 74138 that you connect, you can have a maximum of 64 I/O ports on this particular device.